we're going to start lecture 6. This is page 1 of something. For us, we're going to look at chapter 4 in the Hibbler text. That is where we introduce the concept of the moment. The moment of a force about a point or axis provides a measure of the tendency of the force to cause a body to rotate about the point or axis. In physics, we often call this torque. And a lot of times we'll call this torque. Torque and moment are essentially describing the same thing. A technical difference I've often heard is that torque is often used when rotation actually occurs. Moment is used when the rotation is potential but not actually occurring. I don't know that that's a concrete difference, but that's normally when I've seen the term moment applied. It is often applied in a scenario where rotation is not actually occurring, but the tendency to do so is there, and we need to be able to measure it. Why is that important? Well, many of you are going to go on to take a course in strength of materials or mechanics of materials or solid mechanics or something of that nature. And that is a course where you will begin to look at objects as they begin to deform or bend or change because we're applying a certain amount of force to them. The amount or the point at which they fail is going to be determined by the stress applied to an object or a body, and that stress is going to be directly proportional to the moment, which is determined based on the force. Right? So, roughly in 2 dimensions, in the simplest terms, roughly, if I have on an XY plane here, and I apply some force F, some distance D from the origin O, the moment about the origin, M sub O, the moment about the origin, the moment applied to the origin, would be equal to the force multiplied by this distance D. That is where D is the what we call the perpendicular distance to the point of, I should say, possible rotation. D is the perpendicular distance to the point of rotation, or what we call the line of action of the force. What that means, the line of action And there shouldn't be an or, there should be an and. And so that's an and. Sorry. Line of action. The line of action is a line that passes through this force. It's in the direction of this force. D is a distance between this line of action and the point of possible rotation, where D is measured perpendicular to the line of action to the point of rotation. If that is all true, then the moment about that point of rotation, in this case the origin, is simply equal to the product of force times distance. The greater the force or distance, the greater the moment. Now, if you have somewhere underneath here, you can write an additional point. There is an additional point. Often, under D, the perpendicular distance, this is often called the moment or lever arm. D refers to the moment arm or the lever arm. We often use lever arm when we're talking about torque. We use moment arm when we're talking about moment. Moment arm. I should really put these in PowerPoint slides. I normally don't use PowerPoint when I teach statics, but I'm looking at how bad my writing is, and I really should put these in PowerPoint slides. I apologize. Hopefully you get the idea, right? And use the closed captioning. It's normally pretty good here. What else do we need to know? This principle is demonstrated by the great Archimedes. Archimedes is credited with a quote, and I don't have it exactly right here, and this is translated from his original language, but he's roughly saying something along the lines of, give me a lever long enough and a fulcrum upon which to place it, and I shall move the world. A couple of terms there. Lever, which is what we're referring to is D here, that represents the lever arm, the length of some lever. Fulcrum is the point of rotation. Fulcrum being the point of rotation. Should probably put my phone on silent from the sounds of it. So what Archimedes is saying here, if we were to draw it out here, let's say we have a fulcrum. Again, a fulcrum is a place of rotation. And we give him a very, very long lever. And we put Archimedes out here. This is how I draw people. Fair warning. Archimedes, fulcrum. And we put the Earth over here. Earth, E. What are we saying? Well, we're saying that Archimedes has a weight. The weight of Archimedes, or an amount of force that he can apply. The Earth has a weight. There's the weight of the Earth. And we're saying that there's a distance between Archimedes and his weight and this point of rotation, the fulcrum. Distance for Archimedes. and there's a distance to the Earth. What we're saying is that if the weight of Archimedes times the length of the lever arm which he's using, right, is greater than the weight of the Earth times the distance of the Earth, the Earth moves. Now that's assuming you could have some unobtainium rod here that is strong enough to not break when we apply this amount of torque to it, and you could get it long enough that it would be, the diameter of the Earth would be insignificant compared to this length of that rod, and then something substantial enough to actually hold up under the amount of force being pushed down. None of that's going to happen, not with the technology we have. But the idea is the same. If I put a big boulder, a big rock on this, and I get enough, what we call cheater bar, or enough lever out here, I can get it to move. Right? I can get it to move. I can actually pick something up pretty substantial with a long enough metal rod and just my own weight, if I put a point of rotation far enough away from me and close enough to the heavy weight. And that's the idea here. And that's based off this principle that the moment, the force times the distance, represents the tendency to cause rotation about some point. In this case, what we call a fulcrum, the point of rotation. Pretty cool. Right? Neat concept. Archimedes is a smart guy. A lot of what we do today is based off of what he did long time ago. Very important concept I need to mention here, though. Right? What if this lecture 6, page 2 of something? What if I've got y, x, and I've got some force F. I've got the origin here. What is the moment about the origin in this case? Pause it here if you need to. Think about this. What'd you come up with? Well, what is the distance? Notice that the moment is equal to that force multiplied by its distance, its perpendicular distance. Right? The distance to the point of possible rotation and the line of action of the force. So what is the distance between the line of action and this force and the point of rotation, in this case the origin? Well, notice there's not any. If the line of action of a force, let's write it. If the line of action of a force passes through the point of rotation, no moment is caused. If the line of action for a force passes through the point of rotation, the point through which you're measuring the moment, then no moment is caused by that force. And that's not a bad stopping place. It's a very important concept. You want to make sure you pick that up. You're going to see that quite a bit throughout the rest of the semester. But it's worth really taking a minute and talking about now, and talking about why, right? Why is that the case? Well, it's because there's no distance. If the line of action passes through the point of rotation, there's no distance between the force and that point of rotation. Therefore, there's no moment. All right. See you guys in the next one.